In the previous lectures, I have discussed about the charges at equilibrium or the equilibrium of charges, and we are talking about the various things involving the Coulomb force actually, that is the force acting by mutually two charged particles to each other. But now I like to introduce to you a new concept, that is electric field. So today actually I want to discuss with you about electric field. So what do you actually mean by this electric field? Now before discussing this electric field in detail, now let me talk about something about this field. So what do you actually mean by field in general? In our real life, what we actually mean by this field? Where there is a field, there is associated with a source of this. Without any source, the field cannot be generated. So when we talk about field, I have to talk about a source of this field. Now, which types of source can be? The source can be of any type. Any object can be a source of a particular field, and that field is called the field of that object, which is the source of this field. I can give you an example, like if me, the source of the field that is created by me in this surrounding medium. So in this environment, I can modify the environment. I actually modified the environment according to the requirement of myself. I modified this environment. I put a board over here, pens in my hand, that is a eraser in my hand. So all the things that I created, modified the environment according to me, according to the requirement of me. So the environment that I have created is the field of me at that instant, at this instant. And here the character of this field comes from the character of my teaching. So the field that is created by anything is actually the property of some property that object exhibits that time. So the field is actually the modification of the certain region of space by some kinds of source object. And when this source object is electric charge, then as the name suggests, the field created by it is electric field. But the charge must be at rest. Actually, we are talking about the electrostatic field. If we talk about the gravitational field, you have read in your earlier classes, in class 11, that when there is a mass, then in a certain region of space, it modified. The space is modified by this mass, and if another mass is taken over here, then this mass experiences a force, and that is due to the gravitational field of this mass. And this mass is called actually source mass, and this is the observed mass or the test mass. In a similar kind of way, we can define the electric field also. Instead of mass, here the property of the object is charge. If we talk about a charge over here, Q, and this is called a source charge, so Q sub S, and this source charge will exhibit its effect, its electrical effect in a certain region of space. In a certain region of space, and that space is called electric field. That space is called electric field. Now, actually, theoretically, there is no sharp boundary. If we talk about that, the electric field created by the source charge up to this region is not correct. It can be to in this region also, this region also, this region also. There is no sharp boundary. But the intensity of the field due to this charge QS will goes down as we go the distance increasing. So as we go far away from this charge, then the intensity of this field will be decreases. But you cannot say the field is zero after a particular region, after a particular point. So there is no sharp boundary actually. This is actually inversely proportional to the distance, square of the distance, that is proportional to 1 by r square. Sometimes it will be proportional to 1 by r cube, 1 by r also. That is inversely proportional to r. So we have a source charge QS, and this source charge will exhibit its electric effect in certain region of space, and that space is called electric field. Now, how we can calculate the strength of this electric field? What is the strength of this electric field? If we take a charge QS over here and QS1, if you can say, and here is QS2, then how can we differentiate the electric field between these two charges? What is the electric field? What amount of charge experience, if we talk about another charge which is placed over here and which is also placed over here, then how can we compare that the intensity, electric field that experience this charge Q and this charge Q? We have to introduce a certain physical quantity which can differentiate these two fields in a correct way. And for that purpose, there is two physical quantity are defined over here. One is electric field intensity. Electric field intensity, that is sometimes called electric field only, and this is denoted as E vector. And keep in mind, this is a vector quantity, electric field intensity or the electric field. And the second one is the electric potential. And the second one is electric potential denoted as V, and this is a scalar quantity. Now here in this video, we will discuss only on this electric field intensity E vector. So the first thing is very important, that how can we define this electric field E vector? To define this electric field E, we have to use a test charge or an observed charge Q. So here, this is the QS, and QS is nothing but the source charge, and Q0 is, or QO is observed charge. Now, if this Q0 charge or this QO charge is experienced a force due to this QS, this Q0 is actually observed charge, and this is taken always positive. This is a convention. I'll call you later. This is a convention that Q0 must be positive. But this QS may be positive or negative. But for simplicity, let me discuss that the source charge QS in this time is positive. So this Q0 charge will experience a force in this direction. That is F. So here the Q0 amount of charge experience a force F due to QS. and we cannot calculate this force between these two forces, between this charge q0 and qs. We cannot calculate the force until we do not know the distance between them as well as the nature of the source charge or the distribution of the source charge. This source charge may be a point charge, this source charge may be a line charge, may be a volume charge, may be a surface charge, etc. So according to this source charge, the mathematical expression of the force onto the charge q0 will be changed. So now I don't like to give you an expression of F directly. Instead of, in general, I like to say that the force experienced by the charge q0 is nothing but F. The electric field is defined as the force experienced by per unit test charge or per unit observed charge. This is the force F experienced by the charge q0. So the force experienced by per unit test charge is nothing but F divided by q0. And here please keep in mind that this charge q0 should be vanishingly small. So here actually the correct way of representation this thing is limit q0 tends to 0, F divided by q0. This is the electric field intensity E. This is the definition of electric field E. Now let me discuss what is the physical significance of this definition, of this expression. Here, this source charge, when we take a test charge q0 over here, if this q0 charge is not very much small, if this is a moderately charge or a big charge, big amount of charge, then it will disturb the charge source charge qs, and when this qs will deflected from its position or it will disturb its position, then the field that was created by it will be changed. When there is no q0, then qs was created a field over here in a certain region of space. Actually, when there is a charge, there is a field, but the field will exhibit, or the charge will exhibit its field or its field intensity when we take another charge in this field. But if there is no charge, then also the electric field will exist. And this electric field is a specific type of electric field. There is a certain field intensity, there is a certain direction of this field also. But if we take a charge q0 over here, and if this charge q0 disturbs this charge qs, then the electric field that was created earlier will be changed. So we have to place over here a charge, a test charge. We have to choose a test charge which would not disturb the charge qs. That is the reason that we take this charge q0 as small as we please, that is q0 tends to 0. But sometimes I find that in some textbook they placed over here a +1 charge, +1 unit of charge. But this is not correct actually. If we talk about say +1 coulomb charge over that point, then this is not a very small charge actually. If we talk about the +1 charge, then if we take q equals to ne, then n equals to q divided by e, that is 1 divided by 1.6 into 10 to the power minus 19. That is the order of 10 to the power 19 number of electrons. This is a very big number of electrons, large number of electrons. So that will always disturb the charge QS. So when we talk about the definition of electric field, we should not choose the test charge or the observed charge like this. We have to take a observed charge or the test charge like this Q0, which is tends to 0. There is no definite particular charge. This charge should be as small as we place, and as small as we choose this charge, the calculation of this electric field or the value of this electric field will be so much correct. If Q0 is so much small, then this definition is so much correct. And as this Q0 is increases like this, the definitions will be collapses because this QS will be disturbed. So when we talk about the definition of electric field, we have to keep in mind that this charge should be small. This Q0 charge should be small, and the force per unit test charge will be the electric field intensity. Because we know when we want to compare some physical quantity, we always take that physical quantity per unit actually. Because if we talk about here, let me take an example like this. If we